This section 3 on discrete time systems is a summary of what you've seen in the course of signals and systems. So for the details, you can have a look at the video course Signals and Systems. So what I will do here is give you a brief summary of what we have seen and re-explain or present some of the concepts that are important for this course. Well, in the discrete time domain, it's also possible to represent a signal using a generic representation. It will be represented as, well, a sum of shifted impulse signals. Okay, so we can show this mathematically by using a shifting property, and the shifting property so therefore exists also in discrete time. So remember that we have here an impulse that is located in n is equal to k. So we can rewrite this expression as a sum from minus infinity to infinity, where we replace xn by x with the value of n where the delta is located, so xk delta k minus n. So what we have used to go from here to here is the shifting property, but the discrete time shifting property. Well, here we sum over n. This does not depend on n, so we can take it out of the sum, and we have a sum from n equal to minus infinity to infinity of deltas k minus n. Okay, in order to have a contribution, the argument needs to be 0. So in all these terms, there will only be one term, the one that corresponds to n is equal to k, that is going to give you a contribution, and that contribution will be 1. So indeed we see that we obtain x of k. So this is indeed the generic representation of a discrete time signal. So now we have shown this generic representation using mathematical arguments. Let us have a look at, well, the intuition. So here is xk. This is what you see on the y-axis, and k, the index, is what you see on the x-axis. And let us draw a function x of k. Okay, so we have shown the function for the indices minus 1, 0, 1, 2, and 3. Okay, so here it is shown that you can rewrite x of k as a sum. Okay, let us consider in, well, maybe red, the term that corresponds to n is equal to 0, and this term will be x of 0 delta k. Well, it's a impulse that is located in k is equal to 0, and that has the amplitude of xk when k is equal to 0. So it's this one over here. Okay, so let us now take, for instance, the term that corresponds to n is equal to 1. So that will be x1 delta k minus 1. It's a delta that has been shifted to the right by 1, so it's located in 1, and it has the amplitude of x when k is equal to 1. So it's this one over here, right? And we can maybe take another one. For instance, n is equal to minus 1. So you'll have x of minus 1 delta k plus 1. Okay, so that's a delta located in minus 1, and the amplitude is the amplitude of xk when k is equal to minus 1. And you see that if you consider all the terms, well, of course, you will be reconstructing x of k. In discrete time, we'll also very often impose causality, just as we have done in continuous time. A discrete time process is causal if for a causal input, which means that x of k is 0 for negative k, and a system at rest, this implies also a causal output y of k. Another way to see this is that the process is causal if its impulse response h of k is causal. If an impulse is applied in k is equal to 0, of course the system will not react before k is equal to 0, at least if the system is causal, which means that the impulse response will be 0 for negative k. We have seen that for continuous time systems, we can describe the system, if the system is a linear time invariant, by its impulse response, that is the response to a Dirac impulse with 0 initial conditions. And once you had the impulse response, you could compute the response of the system to any input x of t using the expression y of t is the integral of minus infinity infinity x of tau h of t minus tau d tau. You have, and this is the convolution integral, so it's the convolution of the impulse response and the input signal. Well, you have something very similar in discrete time. Okay, the system, at least if it's linear time invariant, can be described by the impulse response h of k, that is the response to a unit impulse delta k when the system is at rest. And once you have h of k, you can compute the response of the system to any input x of k as follows, and this is called the convolution sum. It's the convolution of the unit impulse response with the signal x of k. Also notice the analogy between the two expressions, the discrete time expression and the continuous time expression. Well, obviously you can go from this expression to this expression here by simply using the substitution. M is equal to k minus n, so obviously n is equal to k minus m. So this is showing that the convolution also in discrete time is commutative. The previous result can be proved quite easily. So we remember that the impulse response of the system is h of k, and now we have to kind of construct the response to x of k, and we remember that x of k can be written as follow. This is this generic representation of the signal x of k. So we'll construct the response to x of k step by step. We remember that the impulse response and the unit impulse response of the system is h of k. So what we'll do now is we'll look at the response of a shifted impulse delta k minus a by this same system, and by time invariance we'll have h of k minus n. So what we'll do here is multiply the input by x of n. X of n does not depend on k, so you can see it as some factor. Okay, and since we know that the system is linear, and more in particular that it obeys the homogeneity law, we'll have at the output of this same system x n h k minus n. So if we take lots of terms like this, we'll be able to reconstruct x of k, and so we'll be able to compute the response to x of k. So now what we'll do is put at the input a sum of the previous terms, right? And it will be an infinite sum, delta k minus n, and this we know is equal to x of k. Well, by linearity, and this time it will be by additivity, we know that if we put xk at the input of the system, what we'll have? Well, a sum of terms like this one. So a sum of n is equal to minus infinity to infinity of xn h of k minus n, and this will be y of k, the response of the system to x of k, and this is this convolution sum, and what we had used here is additivity, so linearity. We have just shown that the response of an LTI system, given its impulse response and the input signal, could be computed as follows. Y of k is an infinite sum, n going from minus infinity to infinity, of x of n h of k minus n. So now what we'll assume is that the system is causal, which means that its impulse response is causal. So h of k is 0 for negative k, and we'll compute the response to a causal input. Okay, so which means that x of k is 0 for negative k. So let us first start by imposing that the system is causal. Then in here all the h's will be 0 for n larger than k. So it does not make sense, if the system is causal, to do summation beyond k. So you can replace infinity with k over here, and if the signal, the input signal, is causal, this means that this one here will be 0 for n negative. Okay, so in the sum here you can start the summation at 0. Okay, so this is how you obtain the result over here. Okay, and you can do the same kind of argument, or use the same kind of argument for this equality over here. What we'll do now is use this convolution sum formula for a system that is described by its impulse response h of k, and h of k is 2 times delta k plus delta k minus 1. So you have an impulse located at k equals 0 of amplitude 2, and then an impulse located at k is equal to 1 of amplitude 1, and it's 0 everywhere else. So this is what the system produces if you put an impulse at the input. And so we are now interested in the response to the following input. It's a step minus another step, okay, that is shifted by 3. So what will be left are 3 impulses, one at 0, k equals 0, another one at k equals 1, and another one at k equals 2. What we can do is look at the interpretation of the convolution sum. We see that both the impulse response and the input signal x of k, they are causal, so the response of the system to the input x of k will simply be a sum going from n is equal to 0 to k of xn h k minus n. So our input is shown over here, and well, maybe have a look at this generic representation. X of k is equal to sum n is equal to minus infinity to infinity of xn delta k minus n. Only 3 terms will be contributing, corresponding to n is equal to 0, 1 and 2. So this will be x0 delta k plus x1 delta k minus 1 plus x2 delta k minus 2, right? So writing this generic representation is kind of decomposing xk in different terms corresponding to different k. So what we'll do is, well, kind of decompose the inputs in its different components and look at the response of these different components, and then at the output add. You can do this because we assume the system to be linear. Okay, so this term, you'll find it over here, and it's given over here. This one corresponds to this delta, and this is what you see over here, and this term over here corresponds to this delta, and it is given over here. We know that the response to an impulse located in k is equal to 0 will give you h of k, that is defined over here, right? So here indeed we have a delta that is located in k, so the response to x0 delta k will be x0 h of k. This is by homogeneity anyway. Here all x0, x1 and x2 are equal to 1. But anyway, the response of this one is given over here. And by time invariance, we can also obtain the response of the deltas located in 1 and 2. The responses will be shifted by 1 here and 2 over there, and then multiplied by x1 and x2. This is again by homogeneity. So now if we want to find the overall system response, what we have to do is add the different responses to these 3 deltas. One is located in 0, 1 and 2, and if you do this, this is what you obtain, right? This is the response of the system to xk that is given over here, and this is consistent with what is over here. You can see here that you have, well, the term that corresponds to n is equal to 0, the term that corresponds to n is equal to 1, and here the term that corresponds to n is equal to 2. You don't need to go any further because xn is going to be equal to 0 for all different n. And you can see also that to compute y0 over here, you only need to consider one term, this term over here, n is equal to 0, and you find the value over here, it's a 2. For k is equal to 1, you need only this one here and this one here, and you add the value that you have in k is equal to 1 here and in k is equal to 1 over here. 1 plus 2, that's a 3, right? And for k is equal to 2, you need the 3 terms over here, and in k is equal to 2, well, you take 0 plus 1 plus 2, and you have a 3. Okay, so using this example, I think you can see the intuition that is behind this convolution sum. We have seen that in continuous time, the system can be described by a differential equation. If the system is linear time invariant, it will be a differential equation that is linear with constant coefficients. In the discrete time case, the system can be described by difference or recursive equations. If the system is linear time invariant, well, we'll use linear difference equations with constant coefficients. A difference equation or a recursive equation uses addition, multiplication, and time shifting operations. It is possible to go from a continuous time description using differential equations to a discrete time description using difference equation after sampling. This will be explored in the next section of the course. A recursive system, or what is called a difference equation, is a relation between the input and the output that takes the form that is given over here. You can see that y of k depends on the past inputs and the actual input, and y of k depends also on past outputs. And the fact that y of k depends on past outputs makes this equation a recursive equation. So of course you will need initial conditions. For instance, to compute y of 0, you need y of minus 1 up to y of minus n. This system is recursive, and it's also called an infinite impulse response system, or an IIR system. This is something that we have shown in last year's course of Signals and Systems, and you can find the details in the associated video course. If in this equation over here all the coefficients are such that this term here disappears, well, we have a non-recursive system, or a system with a finite impulse response. So if there is no recursivity, the equation simplifies to the equation that you've got over here. So y of k depends only on past inputs and the present input. There is no dependence on past outputs, and of course there are no initial conditions as the system is non-recursive. Such a system, well, obviously is called a non-recursive system, but more often it's called a finite impulse response system, or an FIR system. What we have to show is that indeed this system has a finite impulse response. So what you have to do is consider x of k is equal to a unit impulse, delta k, compute y of k. In our case, since we have an input that is a unit impulse, y of k will be the impulse response. Okay, so let us take the expression and replace x by delta, and we obtain delta k minus m. So what we can do is compute h of 0. H of 0 will be a sum from 0 to m of bm delta, and now I will need to replace k by 0, so it will be delta of minus m. So in this sum over here, there is only one term that is going to contribute, so it's the term that corresponds to m is equal to 0. So the term that corresponds to m is equal to 0 will produce B0. You can do this up to h of m. Let's do this. Okay, so Bm, and we'll have delta. We have to replace k by m, so we'll have uppercase m minus lowercase m. And this equation, there will be only one term that will contribute. Well, the case where lowercase m is equal to uppercase m, so this will lead to Bm. Okay, but in between, of course, we had h of 1 is equal to b1, h of 2 is equal to b2, etc. And now let's have a look at what happens after m. So for instance, in m plus 1, so the sum is m is equal to 0 up to m. Bm delta, we replace k by m plus 1 minus lowercase m, and in this sum going from m 0 to uppercase m, there is no term that will contribute because the index is always going to stay positive. Okay, so this is going to be 0, and it will stay 0 for all indices larger than m. So we have shown indeed that the impulse response is finite. So the length of the impulse response is indeed finite. Another way to see this is, well, if we assume that the impulse response is finite, in the sense that h of k is equal to bk for k is equal to 0 to m, and that, well, the impulse response is 0 elsewhere, well, we can compute the response of this finite impulse response filter using the convolution sum that is given over here. Okay, and we replace h of m by its value Bm, and it does not make sense to sum from minus infinity to infinity because here there will be only, well, m plus 1 indices that will be different from 0. So this yields the expression of what is called a finite impulse response filter, or a non-recursive system. In last year's course of Signals and Systems, we had defined a concept of stability for continuous time systems, and it was called bounded input, bounded output stability. Well, this definition can be used also for discrete time systems. We say that a system, a discrete time system, that is LTI, is bounded input, bounded output stable if and only if for any bounded input the output is bounded as well. We have seen in last year's course that a linear time invariant continuous time system is bounded input, bounded output stable if its impulse response is absolutely integrable. Okay, so the integral of the absolute value of the impulse response converges. Well, linear time invariant discrete time system is bounded input, bounded output stable if its impulse response is absolutely summable. Okay, so this gives rise to this condition over here, and notice the similarity. The integral has been replaced by a sum, and the variable t has been replaced by the index k. We have seen in last year's course that a much simpler way to test the stability of a continuous time system was to look at the location of the poles of the transfer functions in the Laplace domain. Okay, if all the poles are to the left of the imaginary axis, the system is stable. There is a similar way to test stability of discrete time systems based on the location of the poles of the z-transform. The z-transform will be introduced in the next slides and is a Laplace transform of a discrete time signal. Note also that an FIR system is always stable because you only have a finite number of elements in the sum, so of course this will always converge for a FIR system. Well, in order to introduce the z-transform, we'll go back to a sampled signal and we take the Laplace transform of that sampled signal and we'll obtain the so-called z-transform. So remember that a signal is sampled by multiplying the signal that you want to sample by the Dirac-Combe. So if we write that down, it's f of t sum k going from minus infinity to infinity of a bunch of deltas that are shifted by kts. This can go into the sum and we obtain k is equal to minus infinity f of t delta t minus kts, right? And now we are ready to apply the shifting property. Notice here that the delta is located in kts, so you can replace f of t by f of kts, and so this is how you obtain this sampled signal. Well, this sampled signal fs of t is a continuous time signal, so we can take its Laplace transform over here. So we can write the Laplace transform of a sum over k of f of kts delta t minus kts. We know that this Laplace transform is linear, so this is how we go from here to here. And then, well, I won't do it, but you should be able to find that the Laplace transform of a delta is equal to 1. You can start from the definition of the Laplace transform, and you should also be able to show that if you have the Laplace transform of f of t and it is f of s, then if you do the time shifting of the function f of t by a quantity tau, well, the Laplace transform will be e to the minus tau s f of s. So this means that this Laplace transform is, this will play the role of tau over here, is e to the minus kts s, right? So this is how we arrive at this expression over here, and we just want to take this e to the power ts s with us and to drag it with us. So what we'll do is define a variable z that is the exponential of tss, and if we do this, we can rewrite the expression here as a sum over k. Remember that k is ranging from minus infinity to infinity. Instead of writing explicitly the dependence on ts, we'll use this kind of short notation f of k, and we'll write this one here using the z that we have defined. So this will give us z minus k, and this will be the z-transform of the sequence f of k. Okay, and you can simply obtain it by looking at the Laplace transform of a sampled signal, and then define the variable z as follows. So this is something that you should be able to obtain by going through this kind of calculations. So if we're given a discrete time signal f of k, right, we can compute its two-sided z-transform using the definition that we have shown here in the previous slide. Okay, this transform is associated with a region of convergence, and the region of convergence is the region where this sum over here will converge. Remember that in the Laplace transform we also had this two-sided Laplace transform, and it was not very useful in solving differential equations with initial conditions. And anyway, what we are doing is, well, considering causal systems, causal signals. So in the same way, this two-sided z-transform will not be very useful, and it is therefore necessary to define a one-sided z-transform. For the one-sided z-transform, we assume that f of k is either causal or that it is made causal by multiplication with a unit step. So the contributions for k negative are all 0, and we can start the sum at k is equal to 0. Again, there will be an associated region of convergence. You will see that everything that follows hinges on the geometrical series. Okay, so this is this sum over here that is equal to 1 over 1 minus q. Remember that this formula is only valid under the assumption that the modulus of q is smaller than 1. Then there is the one-sided z-transform. This is something that you should be able to obtain from the Laplace transform of a sample signal. And remember that once you write this z-transform at some stage, you say that z is written as the exponential of TSS. So there is a relation between the z variable and the s variable. And what we could add here is also the region of convergence of the z-transform of the sequence f of k, and this is the set of all z's that you can write under polar form r e to the j omega, such that the following sum that ranges from 0 to infinity of f of k r, not z, r minus k in absolute value converges. So in other words, the region of conversion of the z-transform of the sequence f of k is the set of all z's such that this sequence here is absolutely summable. We can define the concept of a pole and a zero in a similar fashion than in the Laplace domain. So we are given a sequence f of k, and if we take the z-transform, we'll obtain a rational function in z. This means that f of z can be written as nz, the numerator polynomial, divided by dz, the denominator polynomial. And a zero of f of z is a value of z for which f of z is equal to 0. So obviously it's a value of z for which nz is going to be 0. A pole of f of z is a value for which f of z tends to infinity. That is a value of z for which the denominator polynomial is 0. The poles and zeros of f of z can be complex, but if they are complex, they are going to be complex conjugate pairs, because we assume here that nz and dz are polynomials with real coefficients. And of course there can be no poles in the region of convergence. Remember that the region of convergence is the z for which, well, the sum that is used to compute f of z convergence, and obviously a z where you have a pole is a z where f of z does not converge, so no poles are included in the region of convergence. We have seen in last year's course of signals and systems that if you have the z-transform and you have access to the poles, you can also construct the region of convergence, and we'll of course assume here that f of k is a causal sequence. So what you do is, in the z-plane you plot the poles, and here we'll assume that we have four poles, two real poles, two complex conjugate poles, and then what you do to obtain the region of convergence is take the poles with maximum radius, right? You see that there are two here because they are complex conjugate, and then you draw a circle of this radius. So we'll assume that this is a circle, right? And the region of convergence is the outside of this circle. In this subsection, we start to construct a table of z-transforms that we can use in the course. And we'll start with the discrete unit impulse delta k. So the z-transform is defined in this fashion, and what we do over here is use the shifting property. Well, the delta is located in k is equal to 0, so this means that we can replace k here by 0, so this is 1. So we end up with a sum of deltas, and of course there is only one delta that is going to contribute, the one located in 0, so this is why we have 1. There are no conditions on z for this sum to converge, so the domain of convergence is the whole z domain, right? Now I want to insist that if the signal has finite support, this is clearly the case for the unit impulse delta k, you can always use the definition to obtain the z-transform, and the definition is the following one. It's a sum where k ranges from 0 to infinity of f of k z minus k. So this means f0 z minus 0 plus f1 z minus 1 plus f2 z minus 2, and so on. So in this case here, if you draw the graph of the impulse, the unit impulse, this is what you have, right? So in this sum there will be only one term that is contributing, and it's the first, so it's immediate that the z-transform of the impulse, the unit impulse, is delta 0, which is 1, z minus 0, 1 also, so it's kind of immediate. Okay, so if you have a general function that is of a finite support. For example, this one. Then it's very easy to obtain the z-transform of that signal, right? So we'll assume that this is 1 here and this is 2. Then it's simply 1 z to the power 0, so 1, plus 2 times z minus 1. This is this term over here, plus 2 times z minus 2. So in the exercises that you will have to do, very often, instead of clearly specifying f of k mathematically, it's shown using a plot. Okay, so you have to be able to construct the z-transform, and the easiest thing is just to use the definition. Well, the next function is the unit step. Remember that the definition of the z-transform is the following one. And what we will need over here is this geometrical series. It's a sum that ranges from 0 to infinity of q to the power k, and it's 1 over 1 minus q, but we need the assumption that the modulus of q is smaller than 1. So if we use the definition and apply it to the unit step, this is what you obtain. Of course, the unit step, it's 1 for k positive or 0, so you end up with this expression. And now what you can do is apply this formula. Okay, z minus k, you can see it as z minus 1 to the power k, right? So here q will play the role of z minus 1. So you end up with this rational function that you can rewrite also as z divided by z minus 1. You will see in the course that often we will work with the variable z minus 1, and in other cases we will work with the variable z, right? Remember that, well, this sum is valid only if the modulus of q is smaller than 1. So in order for this to be true, we need here also that the modulus of z minus 1 is smaller than 1, which is equivalent to the modulus of z larger than 1. So the domain of convergence, the region of convergence, is outside the unit circle. Okay, so another way to obtain the region of convergence is to have a look at the pole, and the pole is located, this will be the unit circle, so the pole is located over here. Okay, so we know that what you have to do is take the pole with the maximum radius. Clearly, since there is one pole, it's, well, the pole in 1, and then you draw a circle on that, and it will be the outside of this circle, and this is the region of convergence, and this is also what we had obtained using this condition over here. Also notice some similarities with the Laplace transform of u of t. It's 1 over s, right? You have a pole at the origin, And if you look at the relation z is ETSS, and so here the pole is at the origin. If you plug that in, you have a pole indeed in z is equal to 1. And also the domain of convergence was sigma larger than 0. And if you remember, well, sigma is equal to 0, the j omega axis is mapped to z is equal to 1. Okay, so the being to the right of the j omega axis will become, well, being outside of the unit circle, z is equal to 1 in the z domain. So clearly there are some analogies. Well, let us have a look at the z-transform of discrete complex exponentials of the type that is shown over here. So we'll do this in general for alpha that can be complex. So by definition of the z-transform, this is what you obtain. Remember that, well, the unit step here for k positive or 0 will produce a 1. So alpha k z minus k can be rewritten as follows. And why did we write it like this? But this is because we want to use this formula 1 over 1 minus q, and remember that the modulus of q should be smaller than 1. So this is playing the role of q over here. So this is what you obtain, and again this you can rewrite also as z over z minus alpha. This step from here to here is valid only if, well, q is smaller than 1 in modulus, so alpha z minus 1 in modulus is smaller than 1, and again this is equivalent to the modulus of z larger than alpha. So the region of convergence is outside a circle of radius, okay, the modulus of alpha. Okay, remember here that alpha can be a complex number. Okay, another way to obtain the region of convergence is to have a look at, well, the pole. Okay, suppose here that alpha is real, that you have your pole here in alpha 0.5. What you will do is, well, you have a radius of 0.5 here, that's the maximum radius. Since we have only one pole, you construct the circle on that, and the region of convergence is outside that circle of radius alpha, right? And this is indeed consistent with what we had found over here. So let us look at this a bit closer when alpha is real, right? Remember that we had here z over z minus alpha. This is another way to write the z-transform, and let us have a look at what happens first when the pole is real but positive. Okay, so this is the z domain, so this is the unit circle modulus of z is equal to 1, and let's take the case where we have a pole at alpha is equal to 0.5, and let us take another case where the pole is larger than 1, let's say 1.1. And let us have a look now at the corresponding discrete exponential, real exponential here, because alpha is real. So we can draw this So the x-axis is the index k, and this will be f of k, right? And so let's see what happens here when alpha is equal to 0.5. So 0.5, of course the sequence is causal, so we'll have zeros over here. In k equals 0 it's 1, right? And then in k equals 1 it will be 0.5. In k equals 2 it will be, well, 0.5 to the power 2, 0.25, and so on. And you see that if you continue, well, you have something that is exponentially decreasing. Okay, this is corresponding to a pole that is inside the unit circle, and you'll have to make the link with stability later, right? So we can now have a look at what happens if alpha is outside the unit circle, so it's positive and larger than 1. So obviously the sequence is still causal. You start from 1, then 1.1 to the power of 1, it's, well, 1.1 to the power 2, well, it will be increasing, and you see over here what you will have is something that will be diverging. It will be exponentially increasing with increasing k. So this case will take alpha real and negative, so we can still obtain a different expression of the z-transform if you use the variable z. We'll again show the z-domain with the unit circle. Modulus of z is equal to 1, and in this case we'll take alpha negative. So we'll consider a case here at minus 0.5. Okay, so this is alpha is equal to minus 0.5, and we'll consider a case here where alpha is negative but its modulus is larger than 1. So you're outside the unit circle, and you can kind of imagine that this will lead to a sequence that is, well, unstable, diverging. Okay, so again we can have a look at the response. So this is f of k. We'll start again with the pole here that is inside the unit circle but with alpha negative, and so this corresponds to this case where alpha is minus 0.5. You can see here that the sequence is causal, so of course you'll have zeros over here. In k is equal to 0, you'll start with a 1. Alpha to the power 0 is always 1, and then at k is equal to 1, you'll have minus 0.5. So this leads us to something that is negative. When k is equal to 2, you'll have 0.25, and here something negative. So you see here indeed that the signal alternates sign, but if you would take the modulus, you still have something, right? If you draw it, it's still something that is exponentially decreasing. So this corresponds to the case where alpha is negative but inside the unit circle. So let us have a look at the case where the pole is at minus 1.1. Again, it's a causal signal, so you have zeros over here. In k is equal to 0, you have a 1. Then in k is equal to 1, you have minus 1.1. k is equal to 2, well, you have something that is, well, approximately here, and then here. So again, you have these alternation of signs, but you have something that is globally diverging, and we will see later that it is linked because to the fact that the pole is outside the unit circle. As announced before, the z-transform is a linear transform. This linearity property is inherited from the Laplace transform.